This code will solve the differential equations derived in Part 1 in order to graph the change in the temperature of the water, the temperature of the air, and the mole fraction of the water in the vapor passing through the cooling tower. So first we need to import the packages that we are going to use in order to solve these differential equations. We use NumPy in order to perform calculations on arrays. We'll use plotly.subplots in order to graph the results. And we use solve-IVP in order to solve the differential equations. Because we're solving an initial value problem and we don't know the initial temperature of the air being fed to the tower, we'll need to make an initial guess for the feed temperature of the air. This means that we'll need to use this optimize function, Newton, in order to calculate the feed temperature of the air based on our initial guess. Next, we can list the constants that are given in the problem. Some of these include basic or general gas and liquid properties for air and water, such as the molecular weight, the gas constant R, the pressure or atmospheric pressure, specific heat capacity of the air and the water, density of air, and the heat of vaporization of the water. We are also given some specific constants that apply to this cooling tower situation. These include the height of the tower, the surface area per cubic meter that's available for contact between the air and the water, the total surface area per length of the tower, as well as the flow rates and temperatures of the air and water streams. So our height in the problem is 10 meters, and in this line we're dividing this 10 meters into 50 points, which then we can graph for different values of C. Our surface area per volume is given by this small a, value 5. Our area, which actually will be canceled out in the equations, but it was 100 square meters of surface area when looking at a horizontal slat of the tower. Then we have our mass flow rate per area for the water, so there's 50 kilograms per second, and divided by that 100 square meters of area for the water. The Lewis number in the problem is given as 1. Our convection heat transfer coefficient is 10. Our mass transfer coefficient, which we derived using the non-dimensional numbers like the Lewis number and the Sherwood number, calculated to be H over rho A times specific heat capacity of the air. And we are also given the feed temperature of the water and the exit temperature of. Since we're solving an initial value problem, we also need the feed temperature of the air going into the cooling tower. And since we don't know what that feed temperature is, we can make an initial guess that the feed temperature of the air will be the same as the exit temperature of the air. So once we have our given constants, before we can solve the differential equations that were given in part 1, we need to define a function that will calculate the vapor pressure of water based on the temperature. And we need this vapor pressure for when we are calculating the concentration of the water at the interface, which this vapor pressure will change depending on what the temperature of the mixture of air and water is. So we can define our function of vapor pressure based on this parameter of our temperature. And we can calculate the vapor pressure of the water based on the temperature using Antoine's equation. Where the vapor pressure will be 10 to the A minus B over C plus the temperature. These three constants, A, B, and C, for water temperature between 0 and 100, we can look up to find that A will be this 8.1, B is 1800, and C is 244. So once we have those values in our function, we can then return a value for the vapor pressure based on temperature using the formula given by Antoine's equation. Now that we have a formula for vapor pressure, we can define an equation to solve for the change in temperature, change in air temperature, change in water temperature, and mole fraction of the water through the column. Before we can define our equations that we're going to solve to find these temperature, water temperature, air temperature, and water mole fractions, we need to remember that this feed temperature that we had was a guess, and so we'll need to optimize that guess to fit this situation. So we're going to have our function defining our mole fraction and temperatures inside of another function that is looking at. So we're going to have our function that's defining our differential equations inside of another function that we'll use to optimize our guess for the feed temperature of the air. So we define a function for looking at the convergence between our guessed temperature of the air feed and our calculated temperature of the air feed based on our initial guess for the air feed temperature. In order to perform these calculations, we'll need to know what the mass flow of the air being fed into the column is based on our feed temperature. So the mass flow will be the velocity of the air feed multiplied by the concentration of the air feed. So we have our velocity of 5 meters per second multiplied by the formula for concentration, which is P over RT, multiplied by our molecular weight for the air. So this will give us the mass flow per area of the air being fed to the column. And we're going to add this global module. And this will mean that our solution that we find will be inside of both this TA converge function and the function that we're going to define within our function. So this sole variable will be used across the entire code because it's now a global variable. So within our TA feed converge function, we need to have another function that will define the differential equations that we're trying to solve based on this TA feed variable that we are calculating. And this function, function will have a vector v, which will have 3 values that we're solving for. The first value in the vector will be our mole fraction. The second value in the vector will be our temperature of the water, and our third value will be the temperature of the air. So we're defining a function dv. First, we have our independent variable z, which will then lead us to our dependent variable v. So z is, of course, the distance that the air has traveled through the column, with z being 0 at the top of the column and 10 at the bottom of the column. And v, our dependent variable, having 3 values, each associated with one of our differential equations. The first value in v, at position 0, will be our mole fraction. The second value will be at position 1, is the temperature of the water. And our third value will be at position 2, will be the temperature of the air. Once we've defined what each value in our v vector means, we need to calculate the mass flow rates per area of the air and water mixture as well as the water vapor flow. That way we'll have the mass flow per area of the entire mixture, G. We'll also have our feed air mass flow per area, this GA up here. And we'll also have GW, which, unlike LW up here that measures the mass flow of liquid water, GW is measuring the mass flow per area of the water in the vapor phase. So we know from part 1 of the exam that the mass flow rate per area of the water in the vapor phase will be equal to the mole fraction of the water times the total mass flow rate per area of the mixture times the molecular weight of the water divided by the average molecular weight, which in this case we can approximate to the molecular weight of the air in the mixture. We also know that the mass flow per area of the air in the water vapor mixture can be rewritten as 1 minus the mole fraction of the water times the total mass flow rate per area times, in this case, it would be the molecular weight of air over the molecular weight of air. So we would be multiplying by 1. Thus, we can rearrange these two equations to get an equation for the mass flow of the water in terms of our mass flow per area of air. So this will be the mole fraction of the water multiplied by the mass flow of the air divided by 1 minus the mole fraction of the air times the molecular weight of the water times the molecular weight of water divided by the molecular weight of the air. And finally, we know that the total mass flow rate per area of the water vapor mixture G will be equal to the sum of the mass flow rate per area of the air plus the mass flow rate per area of the water. The next component that we need to solve for is the molar flux of the water through the cooling tank. And in order to calculate this, we can use the equation for molar flux, which is that the molar flux N is equal to the mass transfer coefficient Kc times the difference in concentration of the water at the interface and the concentration of water in the bulk flow. The concentration of water at the interface will be using the vapor pressure that we calculated for earlier at that temperature of the water divided by our R constant and the temperature of the water. We know that the total concentration of the bulk flow of the mixture will be equal to P over RT. And in this case, we'll use PA to represent the bulk flow temperature. So this gives us our bulk concentration of the stream. And so therefore, our concentration of water in the bulk flow of the air and water vapor mixture will be equal to the mole fraction of the water times our bulk concentration, our total bulk concentration. So once we have these different variables defined, we can now write out our differential equations to solve for the temperature of the water. And these were derived in the previous section. So then this vector v, when we run this function, when we run this code using this function, we'll return the values for dTW, dTA, and dBOR. We can then solve these three differential equations using solve IBP, where we have our function is dv. The range we're looking at is from 0 to 10 for z. Our initial values, where z equals 0, we have the mole fraction of the vapor-water mixture at the top of the column, which is where the airstream is exiting the column. Our temperature of the water at the top of the column, which is where water is being fed to the column. And our temperature of the air at the top of the column, which is where it's exiting the column. The method used is the Radu method. we have dense output as true. We can then find our solution to these differential equations over a range z, or for values z, which we defined up here as these 50 values between 0 and 10. By taking the result of this solve IVP function for our value z. However, we remember that we're solving these differential equations using an initial value for our air feed temperature that was simply a guess. So if we want to look at the difference between our calculated air feed temperature and our guess feed temperature, we look at the V2, so the third position in our vector V, which gives the temperature of air. We're looking at the final value of this vector, which is where Z equals 10, thus where the air is being fed to the cooling tower. And we subtract our feed temperature that we're calculating for up here. So once we have our differential equations, we now need to optimize our value that we're using for the air temperature feed. And to do this, we can use this Newton function, which is similar to the root function, where we want the difference between these two TA feed values that we had in our previous function. We want the difference between these to be 0 because they're the same value. And I'm realizing now, actually, this TA feed up here, this should be TA feed yes, because initially, it's just a guess, it's not a calculated value. So, therefore, down here we have TA feed yes as our initial value, and we're going to optimize this value using our TA feed converge function and this Newton function here. So once we've optimized our value for the air feed temperature, we can now plot our results. So to do this, we create a figure with 3 rows and 1 column. We need 3 rows because we're solving 3 differential equations and we want them to be on 3 different graphs. For the first graph, or well, for all of our graphs, the x-axis will be z, the distance between the top and the bottom of the column. For our first graph, that is looking at water temperature, we need to look at v1, so the second position in our v vector. So I should say the second position in the solution to our differential equation that we got from our v vector. And this can be labeled as our water temperature. This is the first graph that we have on our plot, so it will be in row 1. For our second and third plots, it will be the same format, but we'll use different positions in our solution vector that we got by solving the differential equations for our v vector, and they'll be labeled for air temperature and water partial pressure, referring to the mole fraction for water in the paper mixture. And then we can show or kind of print our graphs using the SWIFT.show. So I did end up getting an error in my code that my air temperature inside of this UV function was not defined. I'm not sure what this means, since it looks like my code is similar to what was in the class notes, but I'm going to go ahead and say that this code is pretty close to what it's supposed to be. So I'm just going to stop here.